Okay, things should be getting started recording and transcribing. So go ahead.
Cool, thanks. Welcome everyone to another VC Libs video code review. Let me share out my screen. Okay, so today we are going to be reviewing PR 1877 from our contributor Adam Busior, implementing conditionally borrowed ranges. Casey's on vacation this week. He's already approved this PR. So I'll be doing the final review. And as part of this, I'll be going through exactly what a conditionally borrowed range is, because I have not been paying very close attention to this specific area of ranges. This fixes our issue 1682, where we had every time there's a standard committee meeting, what we do is we go through the straw polls where they've approved issues and papers, and we file issues in GitHub to track everything. This lets us and contributors keep track of what remains to be done. And in this issue, it was an LWG issue that was solved by a paper being voted in. There's a little bit of confusion initially because it looked like a top-level CS+23 feature, but it's actually an issue that needs to be retroactively applied to CS+20. So let's look at this paper over here, Conditionally Borrowed Ranges by Barry Rebson. So there's some motivation. I probably should have read through all this as homework, and I did not. Let's see. Yeah, so there's some history here. Let's just look at the wording. Okay, so there's analysis of all the various views. Okay, so it applies to a certain number of views. So that's the rationale as to why this is only being added to various views. So we've got a new set of variable template specializations. Enabled borrow range is being enabled for take view, drop while view, common view, reverse view, and elements view. Okay, interesting. And it looks like existing machinery that then goes and activates existing machinery. Here's the definition. A range is a borrowed range when you can hold on to its iterators after the range goes out of scope. Okay, that makes sense. It's basically saying that the range itself doesn't really interact with its iterators. So the iterators are really pointing to the underlying stuff. Okay, so then they explain some examples. String view, that's a good example. It just says, like, pointers basically. Yes, same with span. I don't know if that's completely true for span. We're quite picky about our checks in span, but certainly physically span is just borrowing the underlying data. Okay, so let's take a look at the PR. Okay, so the actual. Okay, so it looks like the actual code changes do align with what the standard says, and then the bulk of the PR is test coverage. Okay, so let's get this diff here. Can I split screen it? Is that gonna be horrible? Kind of horrible. Yeah, that's actually pretty horrible. Let me like this. Okay, so we want template class T inline class expert will enable borrow range for take view. Okay, so we start off template class underscore kept a range inline class expert bool enable borrowed range for take view range, and that's defined in terms of enable borrow range for the underlying range. Yes, that's what all of these are defined as. Okay, so that one's good. We got the take view. Great. Next, for drop view, same pattern. And drop view, yep, so we got that one. This one is template class range, class predicate, enabled bar range, drop wall view. We only look at the range. We don't care about the predicate here. Okay, so drop wall view. Yep. And it was, yeah, tpred in the standard. Yep, that's right. Okay, next up should be common view. Here, this is a good example of why when defining code in the library, by default, it's best if the organization of code in the library, in the headers and the source files, follows the standard order unless there's a good reason to do otherwise, like rearranging things could avoid like for declarations or something. That's a good motivation for defining things out of order. Or if we need to define stuff in a central location to be used by many headers, that's a good reason to extract stuff out of order. But if stuff has got to be in a single header like ranges and there's no good reason to permute the stuff, following the standard order is nice because it makes it easier to audit against either the standard or in this case, a paper patching the standard, that all the machinery is there. We've been increasingly disciplined about following this. Casey has actually been a great motivator for in PR reviews. He'll say, oh, why don't you follow, the standard order here? And doing that more consistently in code has made the code easier to follow, which is nice. So that's why we're able to just match these up in order because the existing code already followed the standard order. So here we've got template class range, inline class export bool, common view range. Yep, you got common view, okay. And then finally reverse view and elements view TN. Okay. Reverse view, template class range, inline class export bool. Yep. And then the final one, should always pay extra attention to the last occurrence because we found, I think the was it Viva 64 static analysis blog posts will often talk about how the last line is the one most likely to contain copy paste errors, and I definitely have seen that. So this is template on T and size TN for elements view TN. Template class underscore kept range, size T underscore kept index. Yep, inline class export bool, elements view, range index, name barred range range. Okay, so product code looks good. Look at the context a little bit here. Okay, so in each case, it comes immediately after the definition of the view, which is good, or deduction guides associated with the view. Okay, product code is nice. Let's see, there's no associated feature test macro with this patch paper. Adam Bussier is adding it to the list of papers we've implemented. We're kind of inconsistent about whether we mark all patch papers in YVAL's core or just top level features. But ranges is one that we've mentioned, not only the original paper, but the 20 zillion patch papers that we've implemented on top of it. So mentioning this here is definitely consistent with that. So here I'm expanding the context to see if we're in the CS+20 region. And wow, we did a lot of work for CS+20. Yep, has CS+20, directly controls, scroll down a zillion. So let's make sure we got the right paper number. The one that was voted in was P2017R1. I've seen a lot of typos in paper numbers over the years, so that's why I double check. So we've got P2017R1 in sorted order, conditionally borrowed ranges, all title case looks good. No feature test macro, okay. So product code is great. So now it's just test code. Okay. Casey changed something and then updated or left a comment about it. Okay. So let's see, is this affecting the 6 different views? Yes, so we've got one for each view. Okay, why don't we look at the simplest ones first, which are these, and then look for the more complicated ones. So drop while, which was this one here with the predicate. Here, all we're doing is in this list of using declarations, a using declaration is where you say using qualified name, like using stood cout, whereas a using directive is where you say like using namespace stood, that drags in all the stuff. The ranges tests are interesting because they use using declarations in their test functions typically to drag in individual names. Because some of these duplicate names in the classic STL, like std_prev. So this allows us to focus on testing bits of the ranges code without saying like using all the stood ranges or using stood and stood ranges and then qualifying. So the pattern is different than the rest of our test typically, but it's consistent across the ranges tests. So here we're using borrowed range. The thing I like to check for is these are typically not mentioned in any sort of sorted order, but I have seen some duplicates added in the past, and the compiler will not complain if you say using stood cout, using stood cout. It's like, okay, I guess I'm using stood cout. So here, this is new. We had enabled borrow range before, so that's good. And this is verifying that the drop while view R, its borrowedness is the same as the borrowedness of the underlying view. But it's not testing anything else there. Okay, so that is definitely verifying the variable template. I imagine these other ones are the same. Here we're adding a comma and then borrowed range, not mentioned before. This is for the elements view. Yep, elements view V. Okay, so test the borrowed range of that. And then reverse. Okay. Reverse view of V, yeah, borrow range R is equal borrow range V. Okay. So this is just minimally testing the variable templates, but then these other test files have 16 lines of code each. So let's see what they're doing. Let's see, common view, drop view. I think drop view is a little simpler. Common view is the one that I believe it coerces the iterator sentinel pair to the same wrapped iterator type for use with classic STL algorithms. So I think I remember Casey telling me the common view was actually one of the more complicated, but views in the ranges library, but not one expected to be used a lot in new code. It's more an adapter for existing code. If you had like a classic STL algorithm or an STL-like algorithm in a library you don't control, where you want to use a newfangled range with it, but it insists on having the same iterator type. So let's look at drop and take first, and then look at common. Okay, so usings. I don't completely understand why this is split into, oh, I guess this is listing different powers. This list of using declarations is input forward, byte, random, contiguous. Okay, so this is existing usings. Okay, no duplication here. This starts with the minimal test of the variable template. That borrowed range of R, which is a drop view of V, is equal to the borrowed range of V. Okay, that's right. And then some actual testing. Okay, so this is at the bottom of a test function. Validate a non-view borrowed range versus validate a view borrowed range. Okay, so we start off with a constexpr span using ctat, class template argument deduction. S, which is viewing, or the span is viewing an array of some ints. And then we both do a static cert and then just a plain call of S with only 4 ints. Okay, so test 1 is that function there. Okay, so where is, okay, so we already have code here of test 1. So my question is, why is this different from this existing code we have? If I were using the VS Code GitHub pull request extension, I could see the context easily. Yeah, here we have a constexpr span, SO, only 4 ints. This actually looks identical, and it can be okay to repeat part of a test later on. I've done that a few cases where like first you test like if you're testing like types or something, you could test like all fundamental types and you mentioned null putter T there. And then later you have a test exercising a bunch of type traits specifically for null putter T. And as part of that, you end up repeating one test once, which is fine. You don't need to fully deduplicate everything. Here, this really does look the same. You make a span. In this case, it happens to be const expr around some ints, and then calling test1, making giving it only 4 ints. Okay, so this is the existing coverage. So this is the new coverage. Validated view bar range. So we start by making an iota view, which is going to count integers starting from 0 unsigned long up to the size of some ints. And then we're going to transform each of those values by looking up what's in some ints. So this is a sort of roundabout way of getting every value of some ints. Okay, so that's interesting. And then we're sort of synthesizing elements here. And then this says if we call test1, we get only 4 ints. Okay. So I'm like 80% confident that I understand exactly what's being tested here, but this looks fine. I don't see any inconsistencies. Okay, so we're good. Drop, use take, but range. Okay, so oh no, this is interesting. Okay, yeah, I found a stylistic issue. So in the other, what was it? Drop while? No, it was drop. I had seen these 2 lists of using declarations. I was like, why do we have 2? Why not just chain them together? And I was like, oh, okay, this one has just the iterator powers. So it can be separate and it's kind of arranged in increasing order of strength. That's fine. But here, we again had the 2 lists of using declarations, but borrowed range is now being added to the wrong list. Wrong, and nothing's wrong with the code, but it's inconsistent. This is should just be the range of iterator strength or range strengths, but borrowed range is being added here. Really, it should be added here. It's not a huge deal, but I will comment. Caps lock. Nitpick. There are 2 lists of using declarations here as in other tests. And I don't need to refer to other tests. The first list is for various strengths of ranges, while the second list is for other machinery. To be consistent with this organization, borrow, or I could say ranges, borrowed range should be added to the second or other machinery list. I guess I can mention the views drop one. Yes. Copy that path. See views drop. Compare. Yeah, which had the other order. Views drop, which is following the existing organization, although this occur in the opposite order. Okay, and I could actually just end up pushing a change for this if this ends up being my only review comment. Okay, so there are 2 lists using declarations here. The first list is for various strengths and ranges, while the second list is for other machinery to be consistent with this organization. Ranges borrowed range should be added to the other machinery list. Compare views drop. which is following the existing organization, although its lists occur in the opposite order. Okay. And now here's just the basic test of the variable template, or in this case, it's a concept. Behaves like a variable template here. The bar range of the take view is equal to the bar range of the underlying view V. Yep. And then same pattern, validating non-view barred range at the const per span. Is another span const or const per? And drop. Nope, it was const per. Okay. So exactly identical. Okay, sorry for the scrolling. Okay. Const per span S around some ints. Test one, statics or not. This is our dual mode const expr and then plain runtime testing. So we reuse this machinery to get both, which is nice. And then validate a view barred range, same iota. Yep. Okay, exact same pattern. These, as I understand it, these ranges tests are all structurally fairly similar, but they differ like just enough that it's made more sense to have separate test files that simply repeat patterns of tests rather than having like a single mega templated test that we instantiate for all the different views. So that's why we see a lot of this repeated code. When it's very, very systematic, we often centralize things. And there is a helper header that these ranges tests take. So that's why we're seeing this stuff repeated. It's certainly consistent with the existing organization. Oh, I should have marked that as viewed. Okay, now common view, which is 18 lines. Okay, so adding to the list. Well, this one just lumps everything together. Okay, so range is barred range. That's good. No repeats. Okay, so Casey says stack assert can data R, meaning do we have the data member or the can we call data on it equals contiguous range is effectively a tautology. He's made this condition more precise, so that's why we're removing existing lines. Stack assert can member data of the range, the common range, when we are both contiguous, because if you want a pointer to the data, you definitely need to be contiguous, and you need to know your size. Because if you're contiguous but you don't know your size, like say one of those ranges that wraps like a null terminated string, you're contiguous for sure, but you don't know your size until you iterate through the thing and find the null terminator. So data, I believe, is specified to only exist when you both know the size and you're contiguous. Okay, so that's good. And then next, static asserts that contiguous range R is the same as can member data R. Okay. Then some if const expr, if we have member data and we call it, it should be the same as dereferencing begin and taking its address. Yep. We have a guarantee here in these tests that the range that we're testing is not empty. That's why we can say this. If the range could be empty, then this would not be valid. So an arbitrary code, like if you have a vector, you can't in general say v.begin and then deref it and then take its address. In fact, that's why vector data exists, because you can always call vector data even on an empty vector. For an empty vector, you get an unspecified but valid pointer. Okay, and then additional tests. If you ask can member data of const R, it's the same as asking questions of const v. Yep, just like above. Same test for contiguous range and can member data. Okay, and this is just repeated for constness. And then here we call the helper function added in utility as const that takes a thing and returns it const qualified, but a reference to it. So same pattern. Okay, so that's good. And then finally validate borrowed range. Oh, R and V are defined what, way above? Way above. R is common view of V. V is the underlying view. Yep. Okay. Stacks are borrowed range R is borrowed range V. Okay, so that was different than the other tests, but all makes sense. Okay, so the only inconsistency here I saw was the using declaration. I don't see any other issues here. So I will approve and push a change. Let's see. Before I do that, why don't we read through this paper a little bit more? I want to read the here we go, introduction motivation, just to see if we missed anything. Always going out of order here. Instead of reading this before actually reviewing the paper or reviewing the code. Okay, so if you try to trim a string using ranges find if, yeah, you're looking at the range S and getting iterators B and E out of it. But it fails to compile. Why? Because ranges find if takes a range and some projection stuff and returns a borrowed iterator. So R will deduce as a reversed view. Oh, it's because here this find if call is looking at the string S in reverse to find the last occurrence of something. Okay, so you get a reverse view to a stood string by reference, and it does not satisfy borrowed range, the definition of the thing. Because it's not an L value reference, nor does the reverse view opt into being a borrowed range. That's why we patched it here. So you would get a dangling iterator, because here are the okay, so I'm starting to understand the motivation here. We're making a reverse view, but that's really a temporary. It's going to be destroyed at the semicolon. So the question that the ranges machiner is trying to answer is, can you use this iterator that's returned after the given view is destroyed? And the original CS+20 definition said, whoa, if you destroy this ref view, the iterators if you destroy this reverse view, the iterators you get from it are going to be completely trashed. Invalidated, but that's not really the case, because the reverse view is just wrapping an underlying iterator. If that underlying iterator remains valid, then reversing it's still fine, even if the view, which is just a wrapper around the string holding a reference to it, is destroyed. The iterators aren't. So this is what you would have to write in CS+20, and that's annoying to have to actually name the view and then keep it around. Okay, so that's why these things are being tagged as borrowed, and that's why the defect, yeah. Okay, so that makes sense. And so that that explains why the test code, let me go back to code, what's something that actually added a test, like drop. It's really this new one, this here, that is doing the testing, because here you've got a view, views iota piping through views transform. Yeah, and this previously would fail to compile because test one would go use its iterators. Okay, I think that makes sense. So I'll go ahead and approve this a comment. Great. And offline, I'll go push a change and then approve it without comment and move this forward to ready to merge. Okay, so that's going to implement an LWG issue, which is great. Also, one of the things we do is, because this issue here is labeled with LWG, that directly affects our status chart. So in the status chart, we have a line called LWG resolutions, and this is keyed off of issues that are labeled with LWG. So currently it is at 4. When we merge this PR and resolve the PR, that will go, the labels on the PR don't matter for the purposes of our chart, but that will close the linked issue. It's linked because Adam said fixes number blah, and fixes is the magic word of power. When this issue is closed, the status chart will notice that an issue labeled LWG was closed on so-and-so date, and will drop this line down from 4 to 3. So no additional work is needed on our part to update this chart. We just need to ensure that the issue is properly labeled and that it's properly linked, and that we don't have a lot of documentation around the use of the labels. We do have a checklist for merging a PR. So the checklist says not only should we merge these PRs at the same time, but also make sure that the PR is linked to any issues that it resolves, so that they'll be automatically closed, and then additional procedure around adding labels like fixed and so forth. So whenever I start a batch of merges, I always open up this checklist and I follow it to make sure that the things that we can't automate or can't easily automate, we always do it the same way so that the status charge and other things remain accurate. That'll also update, pull requests and things like that. Okay, so I think that's our PR for today, kind of short and sweet. Does anybody have questions? I don't hear any. Okay, thank you for joining me on this trip through the ranges machinery, where I'm gradually, very, very slowly absorbing this massive chunk of pages of standard use that Casey and Misco and our other contributors have implemented. This is sort of one of the things that is the most challenging over the long term in the libraries, is ensuring that everybody on the team understands different parts of the code base. It's a sort of familiarity that once you've seen a lot of the code and various fixes or how things were added, like this borrow range stuff, as you build up that library knowledge in your head, you can quickly resolve bugs or other issues that are reported because you've seen most of it before. But that has to be sort of manually replicated across every library team member. So whenever I'm, faced with like a huge library or a huge, new addition to the standard, I'm like, I have no idea what's going on here. And it's only through reviewing PRs that, I educate myself about how all this range of stuff works. And then later, when somebody files an issue involving borrowed range or whatever, I'll be like, oh, I saw that, 3 years ago when I reviewed so-and-so PR. And I haven't exactly found a shortcut, but it's definitely a gradual process of learning. Okay, I think we can call that a video CR. Thanks, everyone.